This video will really focus on understanding the different groups or families on the periodic table and their properties and characteristics. If you look at how the periodic table is organized, because of its properties, certain families or groups kind of developed based on that periodic law that Mendeleev originated and then Moseley enhanced. So column 1 are the alkali metals. These are your most reactive metals on the table. Then there's the alkaline earth metals. Then there's this middle section, which is kind of this darker blue. Those are called your transition metals. The purple section under the green section over on the far side, those purple metals are usually called the inner metals. The green section, those are just nonmetals. They're your very abundant nonmetals. Okay, then the yellow are just the halogens, and the orange are the noble gases. So the yellow and the orange are also part of the nonmetals, but essentially the green is the bulk of the nonmetals, and the other two have their own names. So that's kind of the setup of the structure of the periodic table. And then the bottom two rows, that F block, those are the lanthanide series and the actinide series. So as you know, on the periodic table, we have groups or families, and those are the columns on the table, and then the rows are referred to as periods. So the first group or column that's considered to have a name, because all of its properties are very similar, are the alkali metals. They are in group 1, so they're the first column on your periodic table, and up here you see which ones they are. They do not include hydrogen. Hydrogen is in that column because it does have the same electrons in its outermost energy level as the rest of these metals, but hydrogen is not a metal. So it's not considered to be part of the family, even though a lot of its chemical properties will be similar. So in group 1, when it was originally organized, this table was organized because all of these metals were very highly reactive in water, and I will show you a video in class on what that means. They all burn in the air. They all oxidize really quickly, or rust or tarnish are the other terms for that. They're super soft. You can literally cut these metals with a knife, which is strange. They're very, very good conductors, in which case they're used in our life for their conductivity, like lithium-ion batteries. One of the reasons to use them is just because lithium is so conductive. Again, we find a similarity about them after the table was organized. Their electron configurations all end in S1. They have one electron in the outermost valence shell, and that one electron accounts for its reactivity. Your second group are the alkaline earth metals. In many ways, they are very, very similar to the alkali metals. You can tell by the name just how close they were in terms of how we thought of them, but they're the second column on the periodic table. So beryllium, magnesium, calcium, all those guys. They are harder, stronger, and more dense than the alkali metals, but they are not the densest and strongest metals on the table, but they're definitely more dense than their closest neighbors. They have a very high melting point. They're also less reactive than the alkali metals. So when they grouped initially all together, these were the properties that grouped them. And now we know, based on their electron configuration, that all of these metals share 2 electrons in their s orbital, so S2. And now that we understand electron configuration, we can say that we believe alkaline earth metals are less reactive and more dense and things like that, really because of their electron arrangement. Okay, having a full sub-level of those S's, the next closest electron would have to go into the D or the P, depending on which element you're talking about. And going into a new orbital, what we have found was, and what we've surmised, is it's less stable, okay, because it's a new energy level, right? It's a new energy in the sub-level. So once you have a full sub-level, there's a degree of stability here that isn't given in any other ways. So S2, while it isn't a complete orbital level because there's not the P's full 2, there's a little degree of stability here that the S1s don't have, that the alkali metals next to them don't have. So that's how they're different, really, is the S1 versus the S2. Going all the way across the table, the next group that we talk about are the halogens. So the halogens are the second to last column on the periodic table. They're group 17. They are all nonmetals. When you look at them, they're all nonmetals. The name halogen actually means salt former. So by salt former, what that means is when we found salts in nature, they all seem to have halogens bonded to them. So NaCl, right, table salt. But anything that was a salt was actually something bonded to a halogen. So since that's where we first found them, we call them salt formers because it seemed like you had to have one of these to make a salt. These are your most reactive nonmetals, similar to how your alkali metals are your most reactive metals. And kind of similar in concept to the two of them, halogens now have 7 electrons in their outer shell, which means they only need to gain one more electron to have a complete orbital shell, right? So they're very, very reactive as they try to steal that one more electron away from something, where the alkali metals, right? So back 2 slides ago, the alkali metals, column 1, they had that S1, and essentially having just one electron in the outermost energy level, they are very reactive trying to give that electron up. So there's this degree of stability to having S2P6 that a lot of elements are seeming to react in order to accomplish. So halogens are trying to gain one more, so they're at S2P6. And it doesn't matter for the halogens whether they have a D block or not. We find that it doesn't affect their chemical properties because those D electrons just sit there and are almost considered part of the inner noble gas configuration because they don't do anything. The last family you have to be aware of are the noble gases. Okay, we already seem to know because of class and the noble gas configuration, they're column 18. They are, well, originally they were thought to be completely unreactive, so very stable. Right? Part of the name noble gases came from the fact that they're very stable, non-reactive, they don't interact with other things. Now we know with electron configuration, they have the S2P6, so the coveted 8 electrons that fills that outermost energy level. So they don't tend to want to lose or gain any electrons in any kind of interaction because their shell is full. We now have been able to make bonds, especially for the big atoms like krypton and xenon. We've been able to make bonds with them, but for the most part, they don't really make any kind of compound. Noble gases have a lot of practical uses because of their stability and their non-reactivity. We do reactions sometimes in an environment with a noble gas because they will tend not to bond or interact with other things. They're used in some medical devices, to make parties fun with the helium. But they have a lot of practical uses simply because they are so stable and a gas that we tend to use them because of their non-reactivity. That's it for this video. Go ahead and do your form and have a nice night.